今天我会做这个 talk 用英语来讲，为了就是其他的这些观众。Okay, so hello everyone, my name is Fangyuan. I'm a software engineer from VMware. I've been working on a project called PKS since its beginning for almost 2 years now. So today I'm going to talk about load balancing, especially in the context of cloud native. Okay, so here's what I'm going to do. Firstly, I'll give you a brief introduction of all the concepts related to load balancer. Then I'll walk you through the life cycle of a simple packet and point out where and how load balancing is happening. Also, I'll list out all the techniques can be used to implement some concrete solutions. I do think that sometimes it really helps to get your hands dirty to gain a better understanding of all the concepts. That's why I prepared a demo at last to show you how to build a reliable and scalable L4 load balancer by running a bunch of very simple bash scripts. Okay, let's get started. So I'm pretty sure everyone here are already familiar with the term load balancing. But what does it mean in cloud native context, right? So around 5 years ago, I mean, even for now, some big companies are still depending on very expensive boxes to implement this or to fulfill this load balancing functionality. They are great, but they do come with a bunch of disadvantages. First of all, they are very expensive. The upgrade is very costly, and it takes lots of training and money to get the internal working of the very expensive boxes. Also, as our application scales up, it's very hard to meet the HA requirement because the redundancy model here it provides is 1 + 1, which means you have one active load balancer running to serve all the requests, and the other one is standing by. It's also syncing states with this active one. Also, it brings itself up once it detects a failure of the active one, but it's just not good enough, right? Also, if we're using hardware or some software in the hardware to implement this, it lacks the programmability and flexibility for quick iteration, the same way we do for our cloud native applications. Okay, so we like to have our load balancer defined in software. And to scale our load balancer itself the same way as we scale our applications, we want to keep this software as stateless as possible, right? Then we have this scale-up model, which provides N + 1 redundancy. Also, the deployment itself is extremely simplified because we can deploy the load balancer instance the same way we deploy our application. We can just add more load balancer instances to provide a better load balancing functionality. With that help, we can also shard the load balancer instances to provide performance escalation, to implement different SLA, for example, right? Container native. If you think about a vanilla Kubernetes deployment, where you have at least 3 worker VMs, and you deploy this one container that is serving one service. Now you expose this service, and you have corresponding clusterIP service ingress, and before the traffic hits a target container, if you really think about it, it's very likely that it'll hit the VM firstly, and from where the routing decision will be made again, and the request will be routed to the other VM where this container is actually running. So it just adds a bunch of extra latency and overhead, and we don't want that, right? So by being container native, from load balancer's perspective, all the containers are the same endpoints, just same as VMs, right? Then we can cut all the latency and overhead. It's also very important to be the load balancer to be able to interoperate with other cloud services by being cloud native. For example, some security-related features provided by cloud provider, like DDoS mitigation, right? Or caching, like Cloud CDN, or some identity-based authentication. It's also very important to not ask our clients or customers to do any manual provisioning of platform-related resources, in this case, load balancer itself. As customers' application scales up, we want the load balancer itself to be automatically deployed and scaled to be consistent with our application. Also in cloud native world, as we know that our backend containers, they come and go. So it's a highly dynamic environment, right? And to be able to route requests to the endpoints, currently endpoints, we need our load balancer to be highly configurable to adapt to other changes spontaneously. So with all this being said, let's take a look at the basic traffic flow or the lifecycle of the packet. Here, this picture demonstrates a very classic model where we have clients. All the packets are generated in the clients, and before it hits a target backend server, it will reach a middleware called load balancer. In cloud native world, we tend to model independent modules into separate microservices. And depending on how they interact with each other, it can be very complex. But if you really think about it, the service that is making a request is actually acting as a client. So we still have this old classic model where three phases load balancing can happen, right? Client, load balancer, and service. So now let's take a look at them one by one. On client side, if you have complete control or if you have partial control over clients, you can start load balancing already, right? In this case, you can choose to use gRPC by making calls to gRPC library in your application code. And gRPC itself is smart enough to directly routing requests to different backend servers. If you feel like that's too much, okay, gRPC shouldn't be responsible for this load balancing decision, that's fine. They also provide something called look-aside load balancer. So that means this gRPC client can talk to a third-party entity that implements gRPC LB protocol. So it asks this entity for routing decision. Then this responsibility can be fully delegated to the third party. It sounds all good, but the problem is not everyone understands this gRPC LB protocol. So in Istio, the way they expose the data plane is called something universal data plane API, right? So it abstracts out all the data plane in all aspects. So gRPC is also considering implement this universal data plane API. And in that case, the gRPC client will make requests directly to, let's say, Istio control plane for routing decision. And after that, the request will be automatically routed to different backend servers. If you don't have any control over client, let's say you have an application that is an internal service that talks to other services. And in this case, it's a client itself. But you just don't have control over this code, or let's say a jar package, whatever. It runs just fine, and you don't want to touch it. In this case, we can adopt a model called sidecar proxy. I believe everyone are very familiar with this. It's actually the way Istio is leveraging Envoy proxy, right? You deploy proxy together with all the clients. They talk to each other through some local networking or sockets, and then the proxy will make the routing decisions. But most time, we just don't have any control on clients, and most time, load balancing actually happens in the middleware. Of course, our old friend DNS can be used here. You can define a record to map your service name to different IP, or even one IP. In that case, any class can be used. This IP itself can be backed up by different servers that deployed across the world, actually. And depending on where the server is deployed, the request can be routed to the closest location. I'm going to show you later how to do this in terms of VIP and ECMP. So VIP here means virtualized IP, right? Instead of thinking it as something that we assign to a physical NIC or a virtualized NIC on VM specifically, it's more like an abstraction, right? In L4 networking, it's like a name. It's like the DNS name. We can actually map this IP address to a bunch of clusters or a bunch of servers. And ECMP itself, or equal cost multiple path, is a way to scale one IP or one virtualized IP. So the idea is quite simple. Now the cluster is backed up by this router, right? That's serving this VIP. And we have a bunch of routers that are serving the same VIP. We ask these routers to broadcast this VIP to the same upstream router. Then from this upstream router's perspective, this VIP is actually associated with a bunch of next hops, right? So it's able to pick up anyone from the routers and just send the traffic to that because they are all serving the same VIP. The challenge here is how to reduce the connection disruption as the number of load balancer instance and backend server number changes, right? If that happens, we want to keep all the packets from the same stream or same connection going to the same backend server. And consistent hashing is the technique we used here. So it gives you this guarantee that the number of disrupted connections will be at most as n, 1 over n. If the total number of servers is n. It's good enough sometimes. For example, in Google Cloud, this is actually the MacDev. The picture here shows the software called MacDev. It's actually the paper published by Google. And this is the thing that's supporting Google Cloud Networking, right? To them, load balancing is very important, so they don't care that much about connection disruption. But depending on application, sometimes it's very important. So in GitLab, for example, they took some other techniques together with consistent hashing to minimize the number of disrupted connections. With all these techniques, it's all good. But sometimes we still have the limitation that the load balancer instance itself has to be deployed in the same L2 network with our backend servers. I'll give you more details why this is a limitation. But for now, let's just assume this limitation. So now we want to scale beyond this L2 networking, right? We don't want all our backend servers to deploy in the same L2 networking or on the same switch. So the way to do that is very simple. We use encapsulation or just tunneling, right? We wrap the original packet, use another packet, and directly tunnel the connection to a remotely routable server. From service to service, of course, DNS can still be used in VIP, virtualized IP, or clusterIP in Kubernetes term, right? It's mostly implemented using a bunch of iptable rules. In L4, as we know, except IP, we also have port number, right? So here, the port number itself is also part of the address, the abstraction, right? So it's very important sometimes to be able to expose the same port number across a bunch of servers. And when you send a request to either one of the VMs, they can be routed to the same set of containers, right? So it's called nodePort in Kubernetes or routing mesh in Docker Swarm. And they are mostly implementing by something called IPVS, which I'm going to demonstrate how to use it later with a bunch of details. Of course, service mesh can be used here. It provides something fancier like L7 load balancing. For example, it's able to route your request based on some fields or, for example, URL path, right, in HTTP protocol. It's able to route different requests based on your path to different backend servers. So now, with this concept being said, I mean, this concept's just very dry here, and really, talking is very cheap. So let's just get into the demo, right? As we can see from the previous list here, all these techniques listed here, the L4 load balancing is actually the most fundamental building block, right? And that's what I'm going to do, or I'm going to show in this demo, is to teach you how to extend one IP to make it a name or an abstraction in terms of L4 networking. And I'm going to do this by using some widely available open source softwares like IPVS or just dummy interface or BGP or ECMP. Before I start the demo, I'd like to give you a very brief introduction of the IPVS itself. So IPVS is called IP Virtual Server. It's actually something that has existed in Linux kernel for over a decade, surprisingly, right? And it's widely used now in Kubernetes and Docker to implement the things I just mentioned, like clusterIP and routing mesh and nodePort, like that. And what it provides is essentially just L4 load balancing with many algorithms. like round robin, list connection, destination hashing, blah, blah, blah. It's also able to sync states with other IPVS instances so that if one of the IPVS goes down, we can still keep the states. They're doing that through multicast, but it only supports IPv4 now. Now let's start a demo. So in this demo, I'm going to start from the very simple deployment here. Can everyone see the graph here? Or I can just describe what it is. OK, so the top box here, this guy here is the router. So it's actually my laptop here, right? And deploy 2 other VMs. The first one has IPVS running on that. That serves as a load balancer. And this guy here as a server. It runs a very simple Golang HTTP server. And the client here is actually also my laptop. I'm going to make a bunch of requests to this guy here. And the first mode supported by IPVS is called net mode, or networking address translation. Idea is very simple, that when a request comes to the IPVS, the destination IP will be translated to this real server's IP. And the default routing for this server will be set to this guy here. So when the response will be routed back, and the DNAT will be undone, and so the response can be sent right back to client. Now let's see how it works. All right. So here I have the first VM that has IPVS running on that. So and the same box here, I have the second VM. Then I'm gonna start this server, right? So what this step does really is, as you can see here, you do step 2. Sorry, it's too small. It removes the default routing, which is 33.1, which is my router. I want to change it to the 33.2, which is the IPVS VM, right? And also I start this server. It's quite simple, actually. Then I start this IPVS on the first VM, and I add this server into the IPVS. As you can see here, the virtual IP is configured on this IPVS. And we also add the server into the IPVS. Now when a request goes to this IPVS, it's supposed to send a request to the backend server here, which is the other VM I configured. Now let me start the client. So what the client does is it's just making curl requests to the endpoint with a virtual IP. And it sleeps 1 second every time for this 1,000 times, which is hopefully this demo can end in 18 minutes. Okay. Let's see. Oh, great. As we can see, the server starts serving requests here, right? That's all good. Let's go back to the PPT and see what's wrong with that. So NAT is very plain and simple, but it comes with a bunch of disadvantages. For one thing, all the packets for this connection have to go through the same IPVS, right? That's a load balancer. It's not like something everyone sends traffic to that. Let's say you are download a huge file. So in that case, the request itself is way lighter than the response, right? It doesn't make any sense for a response to all go through this load balancer. So that's one thing. The other thing is we also add extra overhead for the critical path here because we need to modify each packet, right? We are doing DNAT here for each packet. Oh, thank you. For each packet. So we would like to let the server send a response directly back to client. And how to do that? Here comes the second mode supported by IPVS, which is called direct routing. The idea is this server here, this IPVS here, will send the packet in L2 directly to this server. It doesn't do any IP level changes. It sends this packet in L2, right? A switch level directly to this guy here. And we have a dummy interface configured on this guy with a virtual IP. Then we configure routing to the default routing to this guy. So the request can be, So response can be sent back to the client. This technique is called directly server return. With assumption that the server has to deploy in the same L2 network with the load balancer. Let's see how it works. Okay. Now I'm going to start a second VM. What this step does is it sets up this virtual IP on the dummy interface. Also, it starts this GoLAN server. And then I'm going to add this server into my load balancer. Okay, as you can see here, this server is added into the load balancer, right? $33.4. If we go to this page here, we can see it starts serving requests as we expect. But you might be wondering why it's only the second server that's serving the request. The reason is the default algorithm is called WLC, or weighted least connection. So the load balancer itself will send all the requests to the server with the least connection. Let me do a watch on the load balancer stats and see what happens. As you can see here, the active connection for the first one is 64. The second one is 55. So the second one is still catching up. And before they reach the same number, the load balancer will send all the incoming requests to the second one. Okay. With this direct routing mode, we just liberate ourselves from the limitation net puts on us, right? The response can be sent directly back to client, and we are okay to download some huge files in this case. But still with the assumption that we have to deploy load balancer and server in the same L2 network, and we want to scale beyond L2. The way to do that is a third mode supported by IPVS called tunnel mode. The idea, just like what I described before, it encapsulates this packet with another packet, and it tunnels this connection to a remotely routable server. So here, the VM is deployed actually in another subnet. If you can see that, it's deploying 34.2. These three are deploying 33 subnet, right? So it's just remotely routable. It's not in the same L2 network. And the way to configure that is to set VIP on this tunnel 0 interface, which is the default Linux default IP interface. Okay, so IP is a protocol used by IPVS here for encapsulation, which means to wrap one IP packet with an IP packet. Let's set this up. Now I start a third server. So what this command does is it just sets a tunnel mode on this server like I described before, and it starts this GoLAN server. Okay. Then I'm going to add it into the load balancer. As you can see, 34.2 is also added into the load balancer. If we go to the client here, oh my god. Well, I don't know what's happening here. It looks like there's some failure, but that's fine because we're going to have health check on the load balancer later in the demo. So now the requests are serving by these servers, even with some temporary failure. Probably because some networking in this building, I don't know. If you look at this picture here, they all have the active connections around 10 or 20. Okay. So now everything is good, right? We are able to scale beyond L2. What's the problem then? If you look at the deployment here, the load balancer instance itself becomes a single point failure. It's a bottleneck here. If this guy goes down, it brings down all the other servers. So we want to scale beyond this IP, this virtual IP that is supported by these servers, right? So the technique used here is called ECMP. The idea is this guy will run GoBGP to broadcast this virtual IP to upstream router. And we are going to replicate this deployment here to have a second load balancer instance with other servers. And the second load balancer instance is going to broadcast the same VIP to the upstream router. So that from upstream router, it actually have two routers with the same, supported by the same VIP. Let me first replicate the deployment here. So now I'm going to deploy two more VMs. Oh. Okay. Oh, nice. I'm going to deploy two more VMs here in different subnets, and then I'm going to have a second load balancer instance. Then I'll set up the second load balancer instance. As you can see here, the second load balancer, oh, sorry. The second load balancer is here with two other servers configured. Now let's say if it works, I'll change the default routing on client to the second load balancer. So now we just change the default routing to 33.5, which is second load balancer, and ideally requests will be routed to the other two servers. Okay, nice. So as you can see, these two guys start serving requests. Okay, and now we want to scale beyond this virtual IP, this two load balancer instance. And we're going to start GoBGP on both instances. So what this command does is, oh my God, is it starts GoBGP on both IPVS, and ideally it should add it should broadcast the virtual IP. Let me run this manually. Okay, so we just started GoBGP on both load balancers, and they broadcast the same VIP to its peer, which is the upstream router. And on this host, you can see the routing table here. It actually has this VIP associated with two next hops. And this guy will pick up one of the two to send out the traffics. And to make this guy work, we need to change the default routing to the upstream router, which is 33.6. And now if you go to here, let's see. Okay, cool. So all the requests are started serving by the first load balancer. But in this case, even if the first one fails, we have no problem because we just use GoBGP to back up this virtual IP by two routers. Okay, let's then mimic the failure here by shutting down the VM. And before that, I'll add some health check. Okay. So health check is very important in the balancer because it needs to detect the failed server to stop sending incoming requests to the failed one. And in this case, we can only support, we can implement the scalability and availability we mentioned before. So let me add some health check on the load balancer. So the health check here is also very simple, some bash functions. What it does really is it makes requests on this endpoint. If it fails, it's going to run this command. If it succeeds, it's going to run the second one. The first one is to remove this endpoint from the load balancer. The second one is to add it back. Okay, so it's going to keep querying the endpoint and either add it or remove it. Now we just started the health check, and we can see the health check request is showing up on these 3 servers. Let me mimic the failure by shutting this guy down. Cool. As you can see here, the third one is removed automatically. And from client's perspective, there's no disruption at all. All the requests are served, right, by these 2. The third one, even though it fails, it's removed automatically by the health check function. And let me just remove the other 2 and see if the traffic switched to the second guy here. Okay, let me shut this guy down. Now it's done, and you can see it's also removed from the IPVS stats here. Let me also shut this guy down. Oh, nice. So there's no disruption at all. As you can see, when I shut this guy, it's 619 or something like that, and all the requests are automatically routed to the second load balancer, right? They are served by this cluster of servers. So if you go back to here, you can see the first load balancer is automatically removed from the upstream router. Okay, so in this way, we just build a very scalable and reliable L4 load balancer. Since we are running out of time, I'm going to stop here. Feel free to ask me any questions. Also, the setup is available on GitHub. If you have any question, you can just ask me or send me any email. Thanks to everyone for joining and bearing with me for this very long demo. Thank you.
So what's the difference between IPVS and the RVS? So what's the difference between IPVS and the RVS?
Sorry, can you see? Well, second one. What's the second one?
LVS.
LVS?
Yes, and another open source load balance.
LVS. I'm not aware of that. Sorry.
Okay.
Yeah. LVS. I think it's just Linux virtual server or something. Maybe they are the same thing. Right? Yeah, they are the same thing. It's just the names are different. It's the same thing. IPVS or LVS. Sometimes they just call it LVS.
Okay, thank you.
Yeah. Any question? Okay, thank you guys.